the last session, we were talking about how to design a combined strap footing. So we have done up to the design, up to the depth requirement and the area of steel requirement. So let us have a brief discussion on what we have done in the last session. So this is the problem statement. We have two square columns which are loaded with 300 and 500 kilonewtons, and the center to center distance between the two columns is given as 4 meters with bearing capacity of soil as 100 kilonewtons per square meter. And what they are telling is we have to design a combined footing by using a strap beam. Okay, this is the condition that they have provided. And another condition that they have provided is we should not use the width of foundation more than 2 meters. That is, we should use the width of the foundation as 2 meters only by using grade of concrete as M20 and grade of steel as Fe415. This is what they have given. So, and then we have started finding out the load combinations, right? And then based upon the loads, we have found out the area of the footings. So then we found out the one-way shear calculation, and then we have decided what is the spacing of the things, all these rough parameters and all. And then we have finally found out the shear force and bending moment diagrams at each and every point. So shear force at a distance of 0 meters, at a distance of 0.12 meters. So all these things we have done with respect to shear force and bending moment. And this is how we got the shear force diagram, and this is what we got the bending moment diagram, right? So now what we are going to do is we need to design a strap beam. Okay, we need to design a strap beam. So let us design the strap beam. So let me keep the heading as design of strap beam. So what we are going to do here is we need to design the strap beam. What is the idea of designing the strap beam? We have two isolated columns, or we have two isolated footings, and we are going to connect these two isolated footings by using a beam, and that beam we are going to call it as strap beam. Okay, that beam we are going to call it as strap beam. Right. So now what is the maximum moment that we have here? If you look into the bending moment diagram, or if you look into the bending moment values, what is the maximum moment that we have among all these values? Forget about the sign convention. We should not bother about the sign convention. The maximum moment that we have is a 211.5 kilonewtons meter. This is the maximum moment. So for this maximum moment, or based upon the usage of this maximum bending moment, we have to decide the depth of the beam. Okay, we have to decide the depth of the beam. Width of the beam we have already decided, which is 300 mm. So how we have decided the width of the beam? We have decided the width of the beam based upon the column dimension. Whichever column is having the larger dimension, based upon the larger dimension of the column, we have decided the width of the beam. So now it's time to decide the depth of the beam. So how we are going to decide the depth of the beam? We need to decide the depth of the beam based upon the bending moment, or the maximum bending moment that we have. So what is the maximum bending moment values among all these four values? It is 211.5. So based upon this 211.5 kilonewtons meter, we have to decide the depth of the strap beam. Okay, we have to decide the depth of the strap beam. So we know the max moment, that is M equals to 211.5 kilonewton meter, right? So from this, we are going to look into the factored moment, which is given as mu equals to 1.5 times of 211.5. So this will be 317.25. 317.25 kilonewton meter. This is the ultimate moment. Now, in order to find out the depth of the beam, okay, in order to find out the depth of the beam, we know that we have to use the depth of the beam calculation based on grade of steel. So for Fe415 grade of steel, what is the grade of steel that we are using here? Fe415. So for Fe415 grade of steel, okay, for Fe415 grade of steel, we know that mu limit equals to, okay, that is limiting moment of resistance equals to 0.138 FCK BD square. This is the formula. So from this value, we need to find out the D value, that is depth of the beam. So mu limit is the ultimate moment, that is 317.25 into 10 power 6. Okay, that equals to 0.138 into FCK. FCK is grade of concrete, that is 20. And B, what is the width of the beam here? B is nothing but width of the beam. What is width of the beam? We have taken it as 300 mm into d square. So if you solve this equation, we are going to get the value of d that equals to d equals to 618.99 mm. That is the depth of the section or depth of the beam. So here, since beam is going to carry huge amount of loads, we are going to increase the diameter of bar. Let's say provide 25 mm diameter bars. We can take any diameter of bars, but I'm just assuming it as 25 mm diameter bars. So 25 mm diameter bars with clear cover or with cover as something like. So usually for beams we are going to take the clear cover as 25 mm. So you can take up to 30 mm also, there is no problem. So let me go with 30 mm with a clear cover of 30 mm. So from this, the overall depth of the section, capital D, equals to effective depth, that is 618.99, plus the clear cover, that is 30 mm, plus diameter of bar divided by 2. 25 divided by 2. So that equals to, we are going to get the overall depth, which will be 661.49 mm. So this one, you can round it off to 700 mm. Okay, I'll be rounding it off to 700 mm. So from this, we can find out the effective depth, that equals to overall depth, that is 700, minus clear cover minus diameter of bar divided by 2. So if you solve this one, we are going to get the effective depth of the section, which will be 657.5 mm. So that's how we have decided the depth of the beam. So width of the beam is, so let me write that, width of the beam equals to 300 mm and overall depth of the beam is 700 mm. Okay, so how this 300 mm based on larger dimension of column, right? So this is how we have decided the dimensions of the beam. Now in the beam, it's a beam, right? So we have to provide the reinforcement inside that. So let us design the reinforcement in the beam. Okay, design for longitudinal reinforcement in beam. So longitudinal reinforcement in the beam. So we are going to design the reinforcement section. So how will you design? So since we are designing the reinforcement in the beam, we have to look after the maximum moment. What is the maximum moment? The maximum moment is 211.5. Okay, the maximum moment is 211.5. So m equals to 211.5 and mu, that is ultimate moment, equals to 1.5 times of 211.5, which will be 317.25. Now, based upon this, we have to find out the area of steel. So we have a formula to find out the area of steel. This one, AST equals to 0.5 FCK by F5 under root of, let me copy that, let me paste it. Yeah. So this is the formula. So from this formula, we have to find out the area of steel. So we know FCK is nothing but the grade of concrete. FCK equals to 20 and Fy is grade of steel, which is 415, and then Mu value. So Mu is 317 point, what is the value? 317.25. Okay, 317.25 into 10 power 6, and then the value of B, where B is the width of the beam. This is what we have talked already, which is 300 mm, and D, which is effective depth. What is effective depth value? So you can see here, which will be 657.5. So D equals to 657.5 mm. Okay, so based on, if you substitute all these values, you are going to get the value of AST that equals to 1609 mm square. Okay, this is the area of steel that we have to provide in the beam. So let's provide the diameter of bar. So I have already told the diameter of bar which we are going to provide in the beam is 25 mm bars. Okay, let us provide that. So provide 25 mm bars. Okay, provide 25 mm bars and with a cover of 30 mm. So let's say area of 1 bar equals to pi by 4 into d square, where d is 25 mm. So pi by 4 into 25 square will give us 490 mm square. That's the area of one bar of 25 mm diameter. Now, based upon this, can you calculate the number of bars required? So number of bars equals to the total area of steel, that is 1609, okay, 1609 divided by area of one bar, which is 490 mm. So if you solve this equation, you are going to get the number of bars as 3.28. So since we cannot provide 3.28 number of bars, I am grounding it off to 4 number of bars are required. Okay, 4 numbers of bars are required. This is how we can decide the number of bars required for a section. So therefore, provide 4 bars of 25 mm in the beam. Right. So this is how we can design the beam. Similarly, we have to design the reinforcement under column 2 and column 1. Why under column 2 and column 1? If you remember the figure of the bending moment diagram or the bending moment pattern, just give me a second. I'm just opening it. Right. So if you observe this particular thing, suppose let's say you have the combined footing like this. We have already discussed about this particular diagram, but anyway, let me talk about this. So if you see this particular combined footing, forget about beam is there or not. So how the bending moment will happen? Bending moment will be something like this, right? So this is how the bending moment will be. So here, since it's a tension zone, okay, this is a tension zone, this is a tension zone. So tension zones where they are occurring exactly under the columns. Okay, under column 1 we have the tension zone, under column 2 also we have tension zone. So since they are tension zones, we have to provide the reinforcement in the tension zone. So let us provide the reinforcement, or let us design the reinforcement under each column. So first let us design the reinforcement under main column, that is column 2. Why I am calling it as main column? Because column 2 is carrying heavy load, that is 500 kilonewtons of load is being carried by column 2. If you see here, the problem yet. So column 1 is carrying 300 kilonewtons and column 2 is carrying 500 kilonewtons of load. So if you design it for maximum load, then obviously you can provide the same reinforcement for the second column also, or for the column 1 also, right? So let us design the reinforcement. So in order to design the reinforcement, so let me call it as main reinforcement, the main reinforcement at bottom support, okay, at bottom support of column 2. Why only column 2? Because column 2 is carrying heavy load. Suppose if column 1 is carrying heavy load, you should design it for column 1 only. And whatever the reinforcement that is coming for column 1, same reinforcement you have to provide for column 2 as well. Right. So now let us look into the bending moment under column 2. Bending moment value under column 2. So that is C2. That equals to, let us see that. So if you observe the bending moment diagram, so this is column 1 and this is column 2. What is the bending moment value under column 2? It is 110 kilonewtons meter. So therefore, bending moment M under column 2 is 110 kilonewtons meter. That's the bending moment value. So ultimate moment equals to 1.5 times of 110. So that will be 165 kilonewtons meter. This is the maximum moment. Now, based upon this, again, we have to calculate the area of steel. So FCK is 20, Fi is 415, and Mu value, 165, and B is the dimension of the column. Which column? Column 2. Okay, that is 300 mm. So D value we know, which is 657 something we got, right? Yeah, this one, 657.5. So based upon this, you can calculate the value of AST. So let me copy this entire one. Right. So if you solve this one, we are going to get the AST value that will be 755.43. And here MU gets changed, which will be 165. 165. Right. So this is how we are going to calculate the area of steel under column 2. Now, if you refer IS code, that is IS 456-2000, there is a statement that is minimum area of reinforcement for beam. Okay, minimum area of reinforcement for beam. So this is based on as per IS 456 2000. As per IS 456 2000, we have a clause which is provided, which will be AST minimum divided by B into D equals to 0.85 divided by F5. This is the formula. Okay, AST minimum divided by BD. Second. AST minimum divided by BD into 0.85 by equals to 0.85 by F5. So what is AST minimum? So we have to find that. So let us find out the AST minimum value. So AST minimum divided by what is B value? B is width of the beam. What is width of the beam? 300 mm into the depth of the beam. So overall depth of the beam is 700 mm. So let me write here it as capital D. That equals to 0.85 divided by Fi. Fi is grade of steel, which is 415. So if you solve this one, we are going to get the value of AST that will be equals to 430.12 mm square. That's the area of steel or minimum reinforcement. How much reinforcement we are providing? 755. So it is within the limits only. So we have to provide 755.43 mm square of steel. So let us find out how many number of bars are required. So since it's a column, let me provide the 16 mm diameter bars. So provide 16 mm diameter bars. Okay, provide 16 mm diameter bars. So area of one bar equals to, that is 116 mm bar, that equals to pi by 4 into d square, where d is 16 square. So if you solve pi by 4 into 16 square, you will be getting the value as 201.06 mm square. That's the area of one bar of 16 mm diameter. So can we find out the number of bars? Yes, number of bars equals to, okay, total area of steel, that is 755.43. Okay, 755.43 divided by area of one bar, which is 201.06. So 201.06. So if you solve this one, you're going to get the number of bars as 3.75. So since 3.75 we cannot provide, we can provide 4 number of bars. Okay, 4 numbers of bars are required. So that's how we can design the number of bars required at bottom support of column 2. Similar diameter of bars, similar number of bars, we are going to provide under column 1 as well. Anyways, we have to design the shear reinforcement. I'll show you that. So now what we have to design is, this is actually main reinforcement at bottom support of column 2. Okay, so this is what we got. So we are going to provide 4 number of parts, right? So now what we are going to do is, so let us find out provided area of steel. So AST provided equals to, how many bars we are providing? 4 bars. Okay, what is area of 1 bar? 201.06. So you will get total area of steel, which will be 804.24 mm square. This is the total area of steel, right? So now what we are going to design is, since it's a beam, so we know that in beams, if you look into beams, suppose if this is a beam, we need to provide the shear reinforcement. Suppose let's say here you have the top reinforcement and bottom reinforcement. So how will you handle, or how will you lock these two main reinforcement bars, that is compression zone reinforcement and tension zone reinforcement bars? We have to provide the shear reinforcement. What does it mean by shear reinforcement? Shear reinforcement is nothing but stirrups. Okay, in beams, shear reinforcement means stirrups. In columns, the shear reinforcement is nothing but lateral ties. So we need to design the shear reinforcement in beams. Okay, we need to design the shear reinforcement in beams. This is what shear reinforcement looks like. So that's the next step, which is shear design in beam. Okay, shear design in beam. So now how to provide the shear reinforcement in beams? So we have to provide the shear reinforcement in 2 cases, where under column 1 we have to provide, and also under column 2 we have to provide. Okay, so let me write that one first. So shear force at a distance D, the shear force at a distance D from interior face of column. Okay, from interior face of column 1. So first let us find out under column 1 and then we'll find out under column 2. Right. So now let us get the value of V, that is shear force. So how to get the value of shear force, that is capital V? V equals to, okay, upward soil pressure. So what is upward soil pressure? Let me check that. Right. Upward soil pressure is 181.82. So upward soil pressure 181.82 into, okay, into, so the depth of the beam, that is 657 something we got, right? So the effective depth of the beam, that is 657.5. So let me write that. So I'll write in terms of meters, that will be 0.6575, okay, plus the size of the column 1. What is size of the column 1? It is 240, right? So 240 mm. So we have to provide that also. I mean, we have to consider that also while designing for shear force. So 240 is 0.24 minus the total load on column 1. What is the total load on column 1? So you can see on 240 by 240 mm column, the load coming is 300 kilonewtons. So let me write that minus 300 kilonewtons. So if you solve this one, we are going to get the shear force value, which will be minus 136.82 kilonewtons. So this is the shear force value. Then ultimate shear force, Vu equals to 1.5 times of, okay, 1.5 times of 136.82. So if you solve this one, it will be 205.23 kilonewtons. This is the ultimate shear force. So based upon this ultimate shear force value, we have to find out tau v, and then we have to verify whether tau v is less than tau c or not. If tau v is less than tau c, there is no problem. If tau v is greater than tau c, then we have to provide the shear reinforcement in the form of stirrups. Let us check whether it is tau v is less than tau c or greater than tau c. So tau v equals to, we know the formula, Vu by Bd. What is Vu value? 205.23 into 10 cube divided by Bd. What is B? B is the dimension of the column. That is, what is the dimension of column? I mean, the maximum dimension, that is 300. I mean, the dimension of beam, not column. So 300 into the effective depth of the section, which is 657, right? Yeah, 657.5. 657.5. That is effective depth value. So if you solve this one, we are going to get tau v value, which will be 1.04 megapascals. Now, based upon this, we can find out percentage of steel, that equals to. So we have got the value of the steel, which is 490 something. Let me check that. Main reinforcement. Let me just give me a second. Longitudinal. Yeah, main reinforcement. Yes, here, this one. Area of one bar. That is 25 mm diameter bar. Right, that is 490. So let me write that. So PT equals to area of one bar, that is 490 mm square. Right. So 4 bars we are providing. So 4 times of 490, that is ASD divided by B into D, that is 300 into D, the effective depth of the section, that is 657.5 mm into 100. So that equals to 0.944, sorry, 0.994 percentage of reinforcement. That's the percentage of reinforcement. So based upon the PT value, we can find out tau c value. So how to find out tau c value? So we know the table 19. So as per IS 456 2000, page 73, if I'm not wrong, page 73, table 19. I remember the table value. So table 19. So if you refer this one, we are going to get PT value. So let me draw the table first. So I have already written the values in my rough calculation, so I'm just directly writing this. So PT and then tau c value. So when PT is 0.750, the tau c value is 0.560. And when PT is 0.994, we have to find out tau c value. And then PT is 1, we have to get the value as 0.620. So based upon this, if you do the interpolation, we are going to get the value of tau c. So tau c equals to, you can do the interpolation calculation, 0.62 megapascals. Now we have to verify whether tau v is less than tau c or not. So tau v is 1.04, tau c is 0.62. So tau v here it is greater than tau c. Okay, tau v is greater than tau c. Tau v is greater than tau c. So what we have to do, we need to provide shear reinforcement. Okay, so hence provide shear reinforcement in the form of stirrups. In the form of stirrups. That's how we have to design. Okay, so we need to provide the shear reinforcement in the form of stirrups. So for this, it's again a different calculation what we haven't seen so far. So we have to find out VUS, that is ultimate shear force, equals to VU minus VUC. This is the formula. Okay, VUS equals to VU minus VUC. We know the value of VU, which is 205.23. Okay, that equals to 205.23 minus VUC. So how to get the value of VUC? So VUC equals to tau c, that is 0.62. Let me write that, 0.62 into B, that is dimension, that is 300, into D, that is 657 point, what is the value? Yeah, 657.5. That's the formula for VUC. VUC formula is tau c BD. Okay, that's the formula for VUC. So that equals to VUS value we'll get, which will be 082.93 kilonewtons. That's the VUS value. Now we have to design which type of stirrup we have to provide, whether it's a two-legged stirrup or three-legged stirrup, four-legged stirrup, or six-legged stirrup. So usually we will provide only two-legged stirrups. So let's say the diameter of the stirrup bar. So provide two-legged stirrup. I hope you know what is meant by two-legged stirrup. So two-legged stirrups will look something like this. Let me draw that. It looks like this. This is a two-legged stirrup. Okay, so we need to provide the two-legged stirrup. So usually the diameter of stirrup is taken as 8 mm. So provide two-legged stirrup of diameter 8 mm. Okay, of diameter 8 mm. So therefore, area of one stirrup. Okay, area of one stirrup with two legs equals to, you will get approximately 100 mm square. This is the area of one stirrup with two legs. Okay, so now what we have to do is we have to find out spacing. Okay, spacing S equals to, that is spacing of stirrup, that equals to 0.87. Okay, 0.87 into Fy, that is 415, into the area of one stirrup, that is 100, into the effective depth, that is 657.5 upon, okay, upon the VUS value, which will be 89.93 into, sorry, 89.93 kilonewtons. I am converting into newtons. Right. So if you solve this one, you are going to get the spacing value. So remember, this is a different spacing calculation than what we have seen in the previous cases. Okay, right. So therefore, the spacing value we are going to get it as 286.24 mm. Okay, and then minimum spacing formula also we have. So spacing or minimum spacing, you can say minimum spacing, right? Minimum spacing equals to, we have a formula which will be 0.87 into Fy into ASV. I'll tell you what is ASV, area of vertical stirrup, that's the thing, divided by 0.4 into B. Correct. So if you solve this one, that is 0.87 into Fy. Fy is 415. into ASV. Area of one syrup is this one, 100 mm square. So 100 divided by 0.4 into B. What is B? B is 300 mm. Okay, that equals to 300 mm is the spacing. Minimum spacing we have to provide. So therefore, I am just rounding it off this value, which will be approximately 250 mm. So provide two-legged stirrups, at a spacing of 250 mm center to center, 250 mm center to center with 8 mm diameter bars. With 8 mm diameter bars. So that's how we can calculate the shear at the distance d from interior face of column 1. Similarly, we have to do the same calculation at interior face of column 2 as well. Okay, shear at a distance d from interior face of column 2. So how to do this? Same. So let me just copy these ones, and then I'll verify. I'll just correct all these things. Right. So shear force at a distance d from interior face of column 2. So upward soil pressure, which will remain same, it will not change, into this one. So here it is 0.6575, but here it gets changed to, let me just check the value. I think it is 1.1 something, 1.1 or 1.2. Let me just check that. Yeah, 1.1. Okay, 1.1. And then dimension of the second column is 300, that is 300 by 2. Right. Let me write that. Just a second, I'm just writing. Correct. So this will be 1.1, okay, the distance plus 0.15, okay, 0.15 plus 0. Effective depth 6575. This calculation you have to cross check later. And then the load coming from column 2 is 500 kilonewtons. So if you solve this one, it will be minus 153.18 kilonewtons. So it will be minus 1. Ultimate shear force will be something like 1.5 times of 153, which will be 229.77 kilonewtons. So tau v value we are going to solve, which will be 229.77 into 10 cube divided by B into D. So B is remains same, that is width of the beam, that is 300, and the effective depth also remains same, which will be 657.5, and then therefore tau v value will be 1.165 MPa. Similarly, percentage of steel. So 4 into 490, that is area of one steel bar, divided by B into D. So this value doesn't change. And then PT value. So tau C, if you solve this one, the value of tau C will be same. It will not change again. And then tau V is greater than tau C. So we have to provide the shear reinforcement. Now let us calculate VUS, that is VU. What is VU value? 229.77. 229.77, okay, into 10 cube. Right. 229.77 into 10 cube minus 0.62 into B, that is dimension of the beam, into the effective depth. So if you solve this one, it will be 107.48 kilonewtons. Similarly, again, two-legged stirrups we have to provide of diameter 8 mm. So spacing will be 0.87 Fy B into D divided by area of steel. That will be, that is not area of steel, VUS value, that is 107.48. This one, 107.48. So if you solve this one, it will be 220.86 mm square. Sorry, 220.86 mm. That's the spacing value. And the minimum spacing, if you solve, 0.87 Fy ASV. So here ASV remains same, and then 0.4 into B, that is also same, which will be 300 mm. So similarly, again, let's say we are going to reduce it to 300 mm. So something like 250 mm or 200 mm we can provide. Let's say 200 mm, I'm reducing it. Okay, so this is under column 2. So that's how we can design the shear reinforcement under column 1 and column 2 in the beam section. So this is the entire design of the strap footing. So if you see the reinforcement diagrams looks like this. So let me copy all these diagrams. You can have a cross check later. Anyways, I'll explain these reinforcement diagrams once when we do the software calculations. Here we have to verify, however. So I'll explain this, but I'm just keeping it for your reference. Right. So this is how this is the beam details. You can see the number of bars, all those things, spacings, all those things, and then the dimensions of the beam, and then here the dimensions of the footings along with the reinforcement details, okay, including the beam. So this is actually the section elevation as well as this is actually in-plan dimensions. That is top view. Okay. So that's the entire design of strap beam. So with this, what we have completed is we have completed the manual design of all the 5 types of footings. So how many footings we have seen so far? So we have seen 5 different types of footings. The first one is isolated square footing. Okay, so isolated square footing. This is what we have seen initially. And then we have seen isolated rectangular footing as well. Isolated rectangular footing. And then we have seen the sloped footing, sloped or trapezoidal footing. And then what else we have seen? Sloped strap footing. Anything else that I have missed? We have discussed 5 types, but what is the other one? I forgot. Let me just have a cross check. What is the other one? So rectangular, square, isolated, combined footing. Yeah. So these are the 5 types of footings that we have completed. So the same 5 types of footings we are going to see in the software design as well. Software design along with Excel sheet as well. Okay, these are the 5 things that we have completed. Right. So from tomorrow onwards, we are going to start the software calculation. So make sure you have the software readily installed so that you can also practice side by side. Right. So that's from my end for this particular session. In the next session, we'll start the software calculation or software design of footings. Same with the same problem statement. Nothing much will get changed. Right. Thank you. We'll meet in the next session. If you have any doubts, you can unmute and ask the doubts.